Rather, the core requirement while designing or considering the infra for data centers is reliability and sustainability. Okay, that achieved through a continuous service. Now, day by day, a lot of activities, commercial activities are being dependent on background, the large data storage, data analysis, uh, edge data centers, edge computing. So this and the way the things are growing, not only reliability and sustainability, but also with a focus on optimizing the capex and the opex for running these infrastructures becomes a priority of key designers. Socomec also has aligned all our businesses and our approach by way of our technical solutions, manpower to meet and align with these requirements of the industry, which is really growing at a rapid pace. UPS systems and power, definitely one of the major concerns in the architecture of data centers. Uh, Various architectures followed today, depending on the size of the data centers and the type of data that they are handling. Uh, and particularly when we talk about the power, here today we will discuss a particular architecture categorized as under a block redundant or a catcher architecture for UPS systems, providing uninterrupted power for your data servers, and also how it benefits compared to the existing proven architectures today being used globally in from edge centers to corporate to co-location and hyperscale data centers, right? So a bit of insight we try to see on this particular architecture compared to the conventional ones, because it's quite proven globally that this architecture has an edge over achieving the above mentioned goals for reliability, sustainability, reducing the capex and the opex. Right? So we move on to take a overview of existing architectures. Before that, also we would like to have these concerns which designers while designing these data centers mainly they will see is eliminating the downtime, optimizing TCO, simplifying maintenance. So these things go hand in hand with while selecting the architecture for data centers from the point of view of resiliency, from the point of view of simplifying maintenance, and the point of view of reducing the OPEX and the CAPEX. So this subject by and large is quite huge. So we will today limit our discussions only to the power supply or uninterrupted power portion. Whole as a subject for achieving these goals is definitely there are various considerations when it comes to data center operations, which team must be aware and they must be practicing it daily. When it comes to power, when it comes to cooling, okay, when it comes to management of the particular data, the service and the operations part. So we will take a quick look today on the uninterrupted power portion in this entire design architecture. How, what is available and what can be considered efficiently in a data center design. So anyway, these are the quite obvious concerns and the approach for designing the data centers. Like for edge and corporate, we know that the scalability is generally designed to be at modular level, and for co-location and hyperscale data centers, the scalability is designed at data level. And of course, the cost optimization approach, what we discussed in the earlier slides, when it comes to deciding the proper architecture and the infrastructure for a co-location or a hyperscale. Now, coming back to the topic of today's discussion, uh, for the uninterrupted power, the various architectures that are followed today, we take a quick overview on what exactly are implemented for the UPS part. Now, one thing is here that we know for generally for co-location and hyperscalers, we talk about tier 3, tier 4 rated data centers, and as per the norms, specified by the Uptime Institute. Although Uptime Institute certification not mandatory, followed by all, but by and large the guidelines under the TI guidelines TI 942. These are generally the architectures what we see which are implemented in co-location and hyperscale data centers globally. The most common being the 2N architecture, commonly called as the redundant systems, two blocks supporting the IT loads. Some basics for deciding this 2N structure. How we do this? Like, take an example, 1200 kilowatt load for a particular data hall. We have this 2N architecture. Now, normal condition, we know these two systems, they will be sharing the loads. However, in case of one system requiring maintenance or any outage, the single system has to support for the entire load. This way, to decide the rating for the UPS in the 2N structure, it will be considered in that what they call the downgraded mode. That is, with one system down, the remaining systems have to support the power. So the obvious equation that becomes 1200 by 1, that is 1200 kilowatt. So we need two systems of 1200 kilowatt in 2N architecture for supporting the uninterrupted power for the particular loads. Now, this 2N architecture, normally the distribution will look like this, that you have two parts. But point to observe is that when it comes to managing or installing the infrastructure for maintaining this 2N architecture, you have to create similar blocks on either side. That is, it's an example of a say 3.6 megawatt data hall. So you need two blocks of 3.6 megawatts on either side. I mean, for establishing the uninterrupted power supply setup here. So this is what is required normally. We take an example of this 3.6 megawatt IT load and a 2N architecture. Now, further we see that, okay, this we just discussed, that in case of outage of one, the one single has to sustain the entire load, and that is how the 2N architecture, we decide the power of N, that is equal to the connected load. Okay. Next is, okay, this is a graphical representation that related to the total power required to be as the installed capacity, right? 3.6 plus 3.6, that is 7.2. The related infrastructure to this UPS systems, like the upstream transformer, the backup power, they also need to be sized for managing these two identical loads. So obviously, the ratings of this transformer and backup gensets also have to be aligned equal to the required capacity of the UPS. Next, architecture that is also followed in many data centers, we see it is like either 4N3 or 5N4. So depending on the size of the servers and the related PUE that the designer or in the operations would like to maintain for a particular setup. So, but we take one example of that as a 4N3 because we found this architecture also quite commonly followed globally. Again, the principle of calculation remains same, right? You see the downgraded mode. In the downgraded mode, that is for installing 4 systems, when you have 3 in operation, they should be able to sustain the connected load. So this means the total power of the installed data hall 1200 divided by 3. There are 3 systems in operation, means each system to be rated for 400 kilowatts. So 4 systems of 400 kilowatt to be installed for managing this 4N3 architecture. At first level of comparison with the earlier 2N, you can see that this is a sizable reduction in the installed capacity of the UPS while managing the same connected load of 1200 kilowatt. Okay. Typically, if you see, this is how the schematic of layout of 4N3 architecture will look like for our same 3.6 megawatt example that we see. Now here, in this architecture, although there is a reduction in the installed capacity of the systems, uh, uh, practically there will be some challenges compared to 2N when it comes to managing the distribution of these four parts, because unlike 2N, now here there are four parts trying to make best use of the dual supply architecture of the servers. So providing four parts for these servers in case outage of any one system, the remaining three will manage the particular loads. So as to say that under normal conditions, these systems will be typically at around 75% load level compared to 50% load level in the 2N architecture. Okay. So in case outage of one, the remaining three systems will take care of the total load. Right. Now, here as a first level comparison, if you see with the 2N, the installed capacity of the UPS systems reduces to around 4.8 megawatt in this 4N3 architecture. And also you can observe the upstream transformer and the backup power requirements also proportionately they can be scaled down. Batteries obviously by default related because of the number of systems being reduced from 7.2 to 4.8. So overall, if you see, this is comparatively an optimized architecture compared to the conventional 2N, where the concurrent savings on the capex and opex are realizable, right? However, as I said, the distribution of these four parts comparatively still remains a complex distribution, which needs to be managed carefully. Right now, the third architecture, what is now gaining popularity globally, that is the block redundant systems. Now, in block redundant systems, uh, these block redundant systems, particularly the catcher application, okay, uh, here, for the particular server loads, this availability is managed in combination along with STS units. So earlier two configurations, we saw that we had redundant UPS systems followed by the distribution system. It may be consisting PDUs or breaker distribution panels. And whereas here in this architecture, you have additional another equipment as a static transfer switch, popularly called as STS, which will facilitate the integration of a catcher UPS. Now, a catcher UPS is as a standby UPS system, particularly. So, in case any maintainability or availability issues with the primary UPS system, the static switch will transfer the load on the catcher UPS. So, this can simultaneously as we designed as a common catcher UPS system for multiple UPS systems, as you can see in the illustration here. Typically, if you see the operations, normally in normal mode, you have these UPS systems as A and B. They supplying the particular loads to the static switch as a normal operation. Which we call a normal path. So any maintainability or service issues on the main UPS systems, the catcher is brought into the picture, and the STS will transfer the load to the catcher as a redundant path. This is the normal operation of a catcher, right? Now designing this catcher as a block redundant architecture, you can decide the capacity of the catcher UPS system, which is fed common to multiple arrays of UPS systems. So in a particular data hall, uh, for multiple sets of server loads supplied by individual UPS systems, using the STS integration, you can have common catcher that will provide as a standby power to all the particular blocks at need base. Now, considering the probabilities of say failure rates, okay, because see these systems are static systems, and there is obviously there is a failure rates, there is a failure rate analysis. So those exercise has been done in detail by experts in optimizing the rating for the catcher UPS. Okay, at first glance, it may seem that a single or two UPS systems may be insufficient compared to the total number of UPS blocks that are installed for the server loads. However, this the resiliency that gets introduced with the additional STS as a component, because STS is not only as a switch that we'll see in the further slides. It has certain properties which gives a value addition to the overall architecture. So a catcher is essentially a combination of the main UPS systems, the standby UPS as a catcher, and the static transfer switches integrated for forming a redundant architecture. Right. Now, uh, while implementing the catcher architecture, you can see here in the illustration there are a couple of methods how this can be done. Now, we take advantage of the servers having the provision for dual inputs, right? Now, when you install a static transfer switch with the main UPS system and a catcher, as shown in the illustration here, there is always a parallel path given to the second input of the server through a switch, right? So now, why this is done? Quite simple. See, the principal working of the STS and the catcher is known and explainable. That in case of any downstream fault or in case of any issues with the major main source, it will transfer to the standby, right? But this arrangement will take care of any unforeseen faults within the distribution system that lies between the STS and the servers, right? So in that case, we have this option of blocking that particular the disturbance, blocking the particular fault condition there using the STS, and the other parallel path can continue providing the power supply to the servers. So this way, the possibility of the main path A not receiving the supply either because of the main UPS system or any intermediate distribution fault, this arrangement will manage to provide the alternate supply to the servers. So this is a typical representation how catcher installation is implemented. Now within this, we have option like we also can include an ATS as shown in the system here, which is interlocked with the particular breaker coming from the main UPS system. Okay, ATS is primarily introduced for the catcher power supply. Right. Now here, this arrangement, like in case any situation that the load has to be transferred to the catcher UPS system, this arrangement still ensures that, as we discussed in the earlier condition, where we try to mitigate the possibilities of any downstream fault to the STS in the distribution system. So now, yeah, so in that case, like suppose if the STS has to be activated for any maintenance purpose or any non-ability of the main UPS system as a situation. The catcher supply will be extended by the STS to the server. That is fine. At the same time, as you can see here, the ATS can also ensure, although there will be an obvious delay, but that delay is not significant because primary continuity of uninterrupted power is maintained by the STS, right? So ATS will still operate, although with some defined delay, and extend the catcher supply to the path B as well. So this is a typical implementation of the catcher architecture using ATS and STS in combination. Alternately, also there lies a option if that depends on the user's choice, where to further increase the resiliency, this supply path B arrangement using ATS can also be replaced with the additional STS. Okay, so this is another option available uh, which can be implemented. Now, if you considering the capacity of the data hall and to really ensuring a still higher resiliency, this option of designing with two STS also is available, right? Principle of operation remains same for both for transfer into catcher if required. Now we take an example of a typical data hall of say 3.6 megawatt as an example with the three UPS systems equaling the required server capacity and a redundant block acting as a catcher. Uh, in case of a situation there happens to be unexpected fault or a plant maintenance on one line, you can follow those green lines and see that the catcher will be supplemented. The catcher will supplement through STS, the UPS power, and continue feeding the load through path A. Okay, so here, although the path B is unavailable, but this architecture can be implemented for a 3.6 megawatt IT load with three UPS systems of 1.2 megawatt each and a catcher block of another 1.2 megawatt. Now, here, as a comparison between the earlier two topologies, we see that the catcher installation requires the UPS systems of a lesser installed capacity, although here you need the additional STS systems and transformers and the backup power for completing the catcher architecture. However, the advantage still remains in this configuration when you look at the availability of the power using this architecture, which in the further slides, I will just give illustration of how the availability calculations also play an important role. As I said, identifying STS not only as a switch, but as a component for improving the resiliency of this catcher architecture. Right. Now, if we see a particular example using a 3.6 megawatt block, say like 10 data halls, each of 3.6 megawatt, this would be look like a typical installation where you can manage two blocks with a single 1.2 megawatt UPS as a catcher. The principle of operation remains same. Here again, the reliability calculations done and model by the R&D teams in deciding the rating of the catcher and the number of UPS systems. It is prone that this optimization is possible having a single 1.2 megawatt catcher for two data halls of 3.6 megawatt each. Now, if you see the comparison, let's say with 10 data halls, right? So when you do this architecture for 10 data halls, you can see in the graphical representation what we saw earlier with a single block and a single catcher, that particular concerns for capex. Here, when you consider this model for a data hall for having a single catcher for two blocks, you can further optimize the installed capacity from 48, which is there in 4 and 3 combination, to 42 megawatt. And this will include the catcher components, what we saw in the earlier slide, which look like an additional component. So the installed capacity, when you compare the capex and the installed capacity, the transformer, the backup power, the UPS, and the batteries all appreciably get optimized in this configuration compared to the conventional 2N and 4 and 3 architectures that are followed, right? So as a general comparison, considering this example of 36 megawatt of total for 10 data halls total, we can see that the installed capacity, which can be brought down to 48 megawatt using a 4 and 3 architecture, can further be optimized to 42 megawatt with along with the STS systems. So, as a quick comparison, you can say that with this catcher option, the equipment capacity is required around 30% less. Around the battery component, which is also a main concern when it comes to the OPEX part, there's 42% reduction in the battery volumes, which are required using a catcher architecture, and also the footprint, almost 38% as a reduction in the overall footprint compared to the 2N architecture required for catcher. This means that overall, using a catcher architecture, we can optimize the electrical infrastructure for a particular for a data center, and it also means that we are looking at a better TCO and a greater sustainability. Now, having seen these slides and trying to understand the catcher composition, which is essentially with UPS and STS in combination, a few slides we will try to showcase here, trying to understand the importance of a static transfer switch, how it plays its role here. Looking at this static transfer switch not only as just a changeover arrangement, but there are certain key features which are quite important when you are selecting the static switch along with UPS systems for catcher. UPS systems, anyway, again, it's a big subject. There are various types of systems available, various proven reference standards, modular, monolithic, etc. Right? However, the static transfer switch also is a component which has certain features, or essentially it should be having certain features which will complete the resiliency expectations out of a catcher architecture for a data center. So what essentially STS should comprise of? As you can see, we will not go dwell into too much of internal details, but as a snapshot, as a minimum understanding of STS, when you look at the specifications for STS, it should be having dual electronic redundant power supplies, meaning not just redundant, but dual redundant. That means you can see that from source 1 and source 2, there are two sets of power supplies which are redundant, which will feed the remaining controllers and electronics in an STS. Similarly, the controller boards also to be redundant within the STS for operations of the static switch, and the respective driver boards also, the driver boards and the redundant, the local power supplies for this particular driver boards, which control the switching element, that is the SCRs. Okay, so as a resilient STS design, these are the essential components which should be ensured while installing the STS along with the UPS in a catcher architecture, because there are options available for normal STS as well, wherein they may have there are models options with say redundant boards, but not dual redundant power supplies. You may have some specs where there will be only redundant power supplies, okay, or some limitations with the driver boards and the local power supplies. So this is something to be ensured when it comes to requirement of an STS. Now look at some important features which the STS should essentially manage. Advanced transformer switching management, or popularly called as a ATSM feature. This is something the USP with Socomec Statis series STS systems. This is a value addition and quite an important feature proven in data center applications, particularly in arrangements where you have downstream PDUs, okay, after the static switch. So in the architecture, you have the static transfer switch followed by PDUs, which essentially has transformers, and then the further distribution up to the servers. invariably, there is a possibility that now why this feature of ATSM is required for situations where downstream transformers. Now, the downstream transformers, as I said, we discussed isolation transfer in PDO. Fine, that is something quite commonly common situation seen in many data center infrastructures. But there also there could be applications where you use a three-wire system for distribution, right? And you use a transformer at the terminal end for generating a independent neutral. So neutral creation transformers, they also can create such a situation, right? While trying to manage a clean neutral for the load side. And a related application for a voltage adaptation transformer. There's some applications apart from normal supplies. There could be some non-standard voltage requirements. So there that this also may arise in introducing transformers downstream to the STS. All in all, when a transformer is introduced downstream and the static switch or any changeover has to happen. Now, this changeover may happen either from UPS to UPS, okay, in a situation where there is no static switch, and if the changeover is taking place from source 1 to source 2, there is a possibility that during such changeover, when the supply changes from source 1 to source 2, because of the residual flux in the transformer, because that changeover happens on the time scale where it is happening based on the required minimum transfer delay. Okay, there here in such a transfer, we are ignoring the residual flux in the transformer, which typically leads to high currents drawn by the transformer during this changeover because of the residual flux. As you can see in the illustration here, this magnetizing current can at times be quite high, and it can be detrimental, creating a risk of tripping the upstream protections. Okay. Now, STS has to have this ATSM feature, trying to mitigate this particular condition, as you can see in the expanded waveform, where the inrush current it can appear during the changeover from source 1 to source 2. Now, with this ATSM feature, the STS intelligently tries to manage this particular inrush current situation by deciding and calculating in the algorithm which is programmed in the STS exactly at what point the transfer should take place from source 1 to source 2, so that this residual flux is mitigated. I mean, this situation is mitigated, and this will not create a challenge when that's transferred on source 2, that it will draw a high magnetizing current by the transformer, because here we are trying to while maintaining the continuity on the secondary side of the transformer, we still try to manage the residual flux within the transformer by intelligently choosing this changeover procedure to mitigate this inrush current risk. As you can see here, this is the waveform that will result when the ATSM feature for STS is in action. Practically, no inrush currents during transfer from source A, from source 1 to source 2, while maintaining the continuity of the power supply. Okay. So now, apart from ATSM, there is another feature for the STS which helps as a value add is that in case of any, as we discussed, the downstream fault, say between the load and the STS, the distribution system, in case of a downstream fault, in a normal condition, this would be directly seen by the upstream source and initiate the tripping of the source or transfer to other source, and maybe propagating the fault to the other source B as well. A possibility that can exist. So with the STS in picture, such fault is effectively mitigated, because the STS, even before the upstream source can react or can see the effect of these fault currents, the STS will block the particular supply, isolate this downstream fault, and prevent propagation of this fault to the other healthy source. Okay. So in a situation like this, typically, as you see, where the STS goes into the blocking mode by sensing the downstream short circuit or a fault current. It will block the supplies, and the STS, which has this source A option, the available as the alternate, will change over to source A, and all the three remaining STS will operate on the source A, and this way effectively isolate and avoid propagation of the fault. So these are some two important features which the STS will add as a value addition in a catcher architecture. So here it is important to understand that the STS does not merely act as a changeover switch for transferring the load from the UPS to catcher, but is an integral part of a catcher design with these features, which gives the overall value addition. A simple illustration here, just try to explain in short. Comparing again between typical a single UPS system and represented by A1 here, and downstream cables, protection and distribution illustrated as A2. So typically for this arrangement, the availability factor calculated at say 99.9%. This improvises further. If you look at a parallel system with similar downstream distribution cables and protections, the availability factor improves to say 99.99%. Now these can be substantiated by proper calculations also. Okay. Now if you compare the third situation what we discussed as a block redundant architecture using catcher and a STS, here you can see that addition of the particular STS in fact increases substantially the availability factor of the entire system to that's as illustrated here from 99.99 to 99.999. Now, in fact, contrary to the concepts that an additional equipment added in the system, additional maintenance, but if you see the resiliency part, managing the downtime in the situation of any downstream faults, okay, the STS plays a key role here along with the UPS systems for ensuring a comparatively better availability factor for the entire setup. So this is what are the concerns and considerations that we would request designers like you and operations team who play a key role in deciding the infrastructure for data centers, and particularly as a power supply infrastructure for upcoming data centers. It would be really positive and in favor of considering the resilient design, a sustainable design, reducing the capex, reducing the opex, that we look at catcher architecture along with STS as a preferred solution for upcoming data projects. Team, this was a short presentation which we had compiled to highlight the catcher architecture options with STS available as a global solution, and more particularly from Socomec. We can interact on these design concerns even in offline with our design team in deciding a proper architecture using catcher and STS systems. If any adapted solutions required, because STS, apart from the two main features which we mentioned, also has some additional programmable features from the point of view of operations, from the point of view of protections. For example, they can be integrated, interlocked with the catcher UPS system for controlling the transfer activity, for preventing the overload on the catcher. Because that is again one concern some of them may have, that a single catcher and so many STS systems and then multiple blocks, whether the deciding the rating of the catcher can be a challenge. But quite intelligently interlocking all the STS systems with the catcher, which is a provision facility available, we can ensure that the catcher actually works as a standby cacher without getting overloaded. Okay, so there are such concerns and considerations that can be followed while designing a data infrastructure using a cacher architecture.